All right. So, similarly to me doing torque management on the 6L90, I also did it for the 4L80. Essentially, I ended up breaking my 456 shaft um, in the 6L90, which was due to nothing more than user error, playing around with settings in HP tuners I shouldn't have, and powering through a burnout, doing a less than 50 millisecond upshift into fourth gear, coming out of the burnout, caught traction, snap the shaft. Pretty common for those shafts to snap on just about anything. So, gotta take my bumps and learn from that mistake. Uh, that transmission had other issues as well, even though it was a remanufactured transmission. So, I'll have to go through it and see if I can find hydraulic issues. The thing had a really tough time learning, uh, and it was very inconsistent in the shifting. And I know someone else running very similar setup to what I have, even with torque management, and their transmission seems to shift better than mine ever has. So I think mine was more of a let's throw some clutch packs at it and not actually inspect for leaks. It came from a warehouse, if you will, remanufactured shop, like a very cheap remanufactured shop. They'll ship it to your door, and it will be there within 3 days. So I wouldn't, I don't know if I would call it non-reputable, but it wasn't exactly like buying from a bigger name in transmissions. It's not like getting something from Circle D where you can really trust what you're getting. So since I never touched the transmission myself, I never bought it. I bought it used secondhand. That's kind of why I did the 6L90 in the first place. It was a good deal. It was going to go in my Volvo project. Decided to play with it in my truck before putting it in the Volvo, and then I found some nuances with it shifting that I didn't really want in my Volvo, but I didn't mind it in my truck, so I kept it. So, anyway, that's the backstory. Ended up hurting my 6L90. 6L90 got put in as well because I blew the rear planetary set on my 4L80. Just kind of happened out of nowhere, but there's metal in the pan for a long time, so I kind of saw it coming. Uh, so anyway, put the 6L90 in it, broke that too. So now I'm on the 4L80. I got a cheap 4L80, and that's why I went back to it. So, what is torque management? Torque management on a lot of OEMs, whether if it's GM, uh, Audi, Mercedes, whoever, right? They all have their own form of torque management, and the way that torque management works is you reduce engine power by one of probably three means um, in order to create an upshift where it's a smooth transition and the transmission clutch packs don't get hit really hard with the transitional torque. Because during that transitional time where you're going from, say, one clutch pack to another or one band to another, uh, that band has to slow down whatever component it is or speed up whatever component it has to with power applied, which is a lot harder than with less power applied. So, BMW with their dual clutch transmission, they cut ignition on the upshift. I know that because I'm doing that swap right now on a different project. Um, and I was reading into a lot of that. The factory 4L80 and 6L 6L90 transmissions, they either do one of two things. They either do a drive-by-wire um, reduction in power, where they'll essentially shut throttle. Not my preferred method, and I'll go over that. Or they do a uh, spark timing reduction, or reduction in spark timing. They retard timing, which hurts engine power. the reason why I don't like the drive-by-wire offset is it's lazy. You know, when you command it to open or shut the throttle, there is a lag time associated with that. Whereas with spark timing, it's instantaneous. You can just control timing whenever you want. So I prefer to do spark timing over some sort of drive-by-wire adjustment. And I tried both with my 6L90, and definitely spark retard's the way to go. So now we'll get on to why I developed it. So I didn't develop it. It's, like I said, it's nothing new, but I needed, or at least I already had, the Terminator X Max on my truck with a 4L80, and I really wanted to. When I wanted to try that 6L90, part of it was because I wanted to see if these two standalones would cooperate together, if I could get some sort of form of torque management to work. So when I got torque management working on the 6L90, and it worked, and it was consistent, and it worked great at the track, I mean, honestly, like, it was very reliable, I said, well, there must be a way to do it with the 4L80. I got to figure this out. It would be kind of fun, especially since the Terminator X Max has a lot of PIDs. It has a lot of data that you can kind of pick up from. It's not as much data as, say, like what the GM computer might have, but at least you have access to it, which is kind of a big deal. So I did it with a 4L80 because one of my struggles with the 4L80 on transmission 1 was I was running a stock torque converter. My truck weighs over 5,100 pounds with me in it, and you know, stock torque converter doing a shift at 6,500 RPMs down to second gear. It's a 40% slip, so you're dropping from, say, 6,000 RPMs down to 45 or 4,800 RPM, something like that. With a loose converter, you don't get as much RPM drop. In turn, the clutch packs tend to actually engage faster because there's just more slip. There's less coupling overall. So everything feels a little bit lazier with a high stall converter. That's my observations now that I have a 3,700 stall converter in a 4L80. So I went from a stock converter to a 3,700 stall, and I mean, I went bigger on pretty much all of the holes for 1, 2, 3, and 4, and it still shifts better than it did with the stock converter because there's just less coupling. So if you think of it this way, this would also work for, say, lockup. Like, say you have second gear, say you want to lock up in second gear for whatever reason. Now your transmission acts a lot like a clutch transmission, like a dual clutch or 6L90 or any of those transmissions with a locked converter. When you upshift, that converter doesn't have that decoupling of a lazy stall anymore. It acts just like a clutch. So when the next set of clutch packs start coming on board for whatever, whether if they're coming on board like with the 6L90 or if it's some sort of a sprag with a band slowdown or the direct clutch is engaging, whatever it may be, you feel that instantaneously through the clutch. So, or because your torque converter is locked up. So one way to help or reduce that shift time is to slow down the input shaft. The way you can slow down the input shaft with a really tight stall converter or during lockup is to reduce engine power. If you reduce engine power, the torque of the load, which is really the momentum of the vehicle, that's your rotating mass, your truck or vehicle traveling at highway speed, that's your torque of the load that's being applied back through the output shaft into the input shaft becomes less than torque of the motor, which would be the engine. So it makes shifting a lot faster because you're having less of a change in torque between torque of the motor and torque of the load. So even pulling a little bit of power, you end up getting faster shifts, which means less friction material in the pan. It also means when those clutches are engaged fully, you run into less of a, you're creating static friction once those clutches are completely stopped. Like once whatever it is that you're trying to stop, um, once it's there, you go from dynamic friction, which has a lower coefficient of friction, to static friction, which is a higher coefficient of friction. So you end up getting more torque handling capability, even with, say, particularly weaker components. So it's best to reduce some power during the shift to let the clutches do their work and get to the next gear and then just reapply power. Now, you can do it one of two ways. You can either reapply power using a like time-based, let's see, like once you're out of torque management mode and it knows you're in the next gear, you could say, for instance, create like a time-based spark reduction. You only pull like say 5 degrees within 0.2 seconds, and you just exponentially drop it down to 0 within that time. That's going to completely soften the inrush of torque to the driveline. So whether you're worried about your drive shafts, your CV axles, if you have like an independent rear suspension car, U-joints, whatever it might be, that's stock, that's like your limiting factor, because there's a bottleneck somewhere, anywhere, whether it's the rods, bending the rods, or the drive shaft or whatever, even the transmission. It's good to take torque out of that shift so you can preserve those components. Maybe you can get another 30 or 40 passes out of a transmission before it turns into transmission soup. So it's best to do it, in my opinion. And for the naysayers that think that pulling timing on the shift slows you down, they clearly haven't seen the sequential guys or H pattern guys that have a strain gauge on the shifter. Those cut timing completely on the shift, so they can make really fast shifts, and plenty of those guys are going quite fast. Between Cletus, that Real Street, their Supra, I think, just went a 6.8, or maybe it was an S2000. I don't remember, but same type of deal. Oh no, Granis Racing. It was Granis Racing. They just went like 6.8 with a sequential, not a sequential, a H pattern. They had a strain gauge on their H pattern. So I believe it was just like a dog box T56 or a faceplated T56. So it's still H pattern. It's a lot like Cletus' setup with a strain gauge. So they just cut ignition during the shift. One, that's for their transmission. They kind of need it because they have to bring RPM down when they get into the next gear. But it shows that if you do it fast enough, you can still have a vehicle break world records and go very fast. So I'm going to get into where we're pulling timing on the 4L80. Unfortunately, I don't have a lot of 4L80 data logs, mainly because a lot of them that I had at the track were on my USB stick. My USB stick has grown a pair of legs and has walked away. I don't know if I'll ever find it again. But I have logs from a 6L90, which illustrates the exact same thing. So I will show you that. Let's see. Oh, well, that's not useful at all. Give me 1 second. All right, sorry about that. Now I'm back. Got my data log here. This one's from 6L90. Red here is engine RPM. This magenta line here, I think I got my coloring right. My girlfriend would be proud. This is Translip. And I'll go over what Translip is in a second. And then the line coming down back to 0. You can see it starts at about 33%, comes back down to 0. You can see this green line here. This green line is torque management. So this is me just pulling timing. In this case, I was only pulling 3 degrees of timing, which isn't a lot, but this is the data log I happen to have. I play with the numbers a lot, so trust me on this one. Get rid of that. What's this? Let's get rid of this. So you can see I'm actually pulling timing through here as well. Let's see, it starts about here, goes about there. Oops. And we'll go back to torque management. So, as you can see where torque management is, despite what the number says. What we really care about here is pulling timing in the right area. You can see here on transmission slip, this right here, where it starts is actually when the command goes out for the next gear. Now with this being on my 6L90, I'm pretty sure this was a 2-3 shift. Pretty sure. It's either a 1-2 or a 2-3, but either way. So when the gear command goes out, essentially you'll have, you meet those wickets, you meet those boxes for part throttle or full throttle shift or whatever, where it's at X RPM and, you know, X speed. When you hit those wickets to create the shift, the command goes out. Well, obviously nothing in life is instantaneous, and that's no different for the transmission. So the transmission has a delay. That's why you have to lead shifts on every transmission. It's less prominent on the 4L80s and the 4L60s, but on the 6L90s and 80s, it's longer delayed because they have to fill clutch packs before they actually try to command the shift. It's all like an algorithm-based shift. There's no real sprags or anything. It's not a dumb transmission where you just throw hydraulic fluid where it's supposed to go and things happen. So this is actually kind of a better example because you get to see how long the delay can be and why it's so needed on the 6L90. On the 6L90, I mean, we're talking almost a full second, like 0.8 seconds or so of time between I command the shift to, you can see how it starts going down this ramp. Well, that's it actually starting to grab the oncoming set of clutches, because when you command that shift, you're creating a slip error. You're saying, whoa, 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 I'm supposed to be in second gear. I know what my gear ratios are for second gear, and my engine speed is not at, say, it should be right now, like say 4,500, or input shaft speed should be at like 4,500. By the way, input shaft speed doesn't show up on this, just so you know. So, and that's just because the 6L90 actually just sends out a translip signal as an input. I don't have to calculate it, which is what we'll go into the 4L80. But on the 4L80, or on any of these transmissions, this delay here is it pretty much, I've commanded the shift, you're not there, and input shaft speed is not there, it hasn't slowed down, therefore we have a slip percentage. Now, as it starts to slow down, that's when we want to start That's when we want to start to pull timing. We don't want to pull it here because you can see the engine's still accelerating. The vehicle is still accelerating. We're still in that gear until we actually start to transition. And that's what the 6L90 and 80s are looking at as well. They're looking at the exact same thing that I'm looking at. And that's actually how they determine when to start venting off pressure from the offgoing clutch pack. So when you do like a 2-3 shift, that clutch pack, the offgoing clutch pack, still has pressure, and you can watch it in HP tuners do this. It will hold pressure on that PCS until it starts to see translip go away. Once translip starts going away, it goes, now I know I've started to engage. bring on the oncoming, let off the offgoing. So it'll pressurize the oncoming, depressurize the offgoing, and then you end up with a nice smooth transition. Hopefully everything's good and you achieve that all within the shift time. Now you can see that being done here, and essentially I set up this table so when I'm in this box up here, when I am in this static error, in other words, it hasn't begun to slow down the input shaft speed yet, I don't want to pull timing here. I don't want to pull timing until I start having it go down. And my window is actually better on the 4L80 than it was on my 6L90. This was one of my very early logs for the 6L90. So I had the tolerances set very, very loosely, and I didn't pull out like any timing because I was trying to learn it. So on my new one for the 4L80, it pretty much starts pulling as soon as input shaft speed slows down, even a little bit. So this line here, as soon as it starts, that's when it will start to pull timing. And now the timing is all set by you. Like you set however much timing you want to pull, and that's in the HP tuners, the Holley bass map with the bass tune, but it's adjustable. You as the end user can adjust it to whatever you need. If you have a very tight torque converter, you're probably going to want to pull more timing. If you have a loose torque converter, you're not going to need to pull a whole lot. A lot of people don't pull it at all, and that's fine. That's up to them. But I still pulled a little bit on mine just because I would prefer to keep my stock transmission as happy as possible, especially in the weight of my vehicle. Now, you can see here, I'm only pulling timing, and this isn't actually 100% accurate because of the refresh rate. These lines here, if you were to go up top where it says time, that tells you about your refresh rate. So you can see it's about 25 thousandths or so, 27 thousandths of refresh rate right now. And there we go, there's 26 thousandths of refresh rate. So this line, it doesn't look as straight as this in reality. It's just, this is what you see. You get what they give you. And that's all just based on refresh rate. But at the computer is doing this incredibly fast. All these calculations are just about real time. Everything's done real time. So we'll go to the Terminator X. Now this is my 4L80E base. I'm going to include this in the Google Drive as well as a Excel sheet that I devised. So we'll go to, I pretty much left everything blank except for what you need. I realized with the 6L91 it might be easier to lose people in that. So I want to start off with Translip. Translip is what's needed to create our torque management trigger. It all starts here with Translip. So this is actually where we need the calculator. This is what you'll be getting. Yep. All right. So this is all auto-filled, and it's actually set up right now for a 4L80. Projected speed is already filled out. You can change gear ratios here if you have custom gears, and it will change all of this to what you want it to be. There you go. Let's go to Translip. So ideally with Translip, you're looking for, it's a comparison between input shaft speed and output shaft speed. If I'm commanding first gear at X amount of RPM, my output shaft speed should be X. Well, or it should be Y. Holley doesn't have a output shaft speed PID, so we developed that using speed. We essentially just reverse engineer or reverse your rear gear size or your rear gear ratio and your tire size to come up with what your min and max speeds are. We plug that into, that all pretty much ties into projected speed. I'll go over that. Projected speed is output speed. That's essentially our, this is what we're going to compare this against. So we're going to take speed, so this is going to be your actual rear wheel speed, and we're going to compare that against projected speed. Projected speed is going to be fourth gear at, say, 8,000 RPM. That's going to be 100% of your total usable speed. 500 RPM in first gear, 1.89% of that usable speed. So we're going to compare that against Translip, and you can see if projected speed, if you calculated this all out, there's a app on Block Layer that'll do this for you, but I did all the math for you in this. You don't have to touch anything in here. You just drag and drop this stuff into the table whenever you need to make changes or whatever. You just copy, paste. The Holley's going to show less numbers in this, like, so for this cell it might show like 96.35, but in reality what it's going to calculate based on is something above that digit. I can't completely prove it, but I just know it makes a difference. So we know at 100% projected speed, we'll be at 8,000 RPM input shaft speed in fourth gear. That's our 100%. Well, if you go to the Block Layer calculator online and you plug all of that in with my tire size and gear ratio, we know that max speed would be 294.985 miles an hour. Now, at that speed, I have no slip. So you can see how this sort of works. Now, the reason why the gear ratios are important is, say I'm doing, here we go. Say I'm doing 8,000 RPM in first gear. I have a projected speed of 30.24. And then I command second gear, but my speed hasn't changed yet. Okay. So at 30.24, just as a rough estimate, we'll save this cell, for instance. So 30.24, roughly, I'm doing 102 miles an hour in first gear. It's a little bit less than that, but we'll just say fine, 95 miles an hour. So we're doing 95 miles an hour in first gear at 30.24 for projected speed. Now, when I shift to second gear gets commanded. Like, that's going to show up as AT gear. It's going to be now in 2, but we haven't changed speed. So in reality, we see we're up at 50.67. Input shaft speed hasn't changed. We haven't started changing any gears. There we go. So you see at about 50 or so, we're at about like between 38 and like 41% slip. That's actually why you see this isn't like a complete linear calculation. Like, you can see numbers down here as low as negative 5290. There was a formula that I developed for this that made a lot of sense. I don't remember what it is off the top of my head, but just trust me when I say it works. It's very consistent. You still get Translip. Whenever you upshift, it's going to tell you whatever it is based on the gear ratio change. So like a 1-2 shift, I think it reads 41% is what you end up seeing, which when you calculate out, let's see, 1 minus 1.48 divided by 2.48, those are your gear ratios. Oh, forgot to put brackets in. 1 minus 0.48 divided by 2.48. Why did it not take my brackets? Let's put it on my phone. I'll just show the screen. Yeah, come on. Why doesn't this want to work? Oh, you know what? I forgot. There we go. Parentheses. It works that time. There we go. Oh yeah, then multiply it by 100 for percent. So 40.32%. You can do the same going to, say, second gear. It should be 33%, just to make sure I got that right in my head. 1 minus 1 divided by 1.48. And then times 100. So 32.43%. And you'll see that on in the data logs. It'll show you when your gears commanded. It'll say, like, say you're going from first gear and then it goes 2. And as soon as it goes to 2, you'll see the same thing that you see in the Holley data log. You'll see Translip come up. And then once it starts to engage, even with the 4L80, that's when you'll start seeing the shift. Now the cool thing is, if you really want to, you can take the measurement between here and here, and you can see what your real shift time was without any sort of guesswork. So that's nice. Now, got some of this stuff out of the way. You have to plug this in based on whatever's in the Holley. So if you go into the Holley, go to the transmission ICF, and you change speed calculation here, you need to change it in this here. Say I went from 33-inch wheels. Let's say I changed my gear ratio in the back and I went to 4.11s. It's going to change. Nothing here will change. Like this will all be fine. This axis will stay the same, but speed, that's going to change. So you need to copy this and you'll paste it into here, which I think I'm in the wrong spot. I am. Translip. There we go. There you go. So you go down to here to speed. Boom. There you go. Now, these are all labeled based on whatever outputs they are in the Terminator X. So you go to Terminator X, go back, you can see projected speed, translip, shift detection. Translip, I'll just move it just for the sake of doing it. So projected speed, translip, shift detection. Oh, by the way, if you change any of those gears in here, you have to do the same. So if you change it to custom and change it here, you have to change it in this as well, and then that'll change these ratios and everything will match up and it'll be kosher. Now, on to the meat and potatoes of how it works. So Translip, we developed Translip using projected speed. Projected speed is ideal speed, in other words, and it's based off of AT gear and input shaft speed. If I'm in this gear and this input shaft speed and go to the transmission ICF and I'm multiplying it by that ratio, I should create X speed, right? And it's going to be in a ratio of 0 to 100% of maximum speed. Maximum speed is dictated by whatever number is put into your input shaft speed in this column. So if I were to say put 9,000, well, it would still be 100% here. But my number down here in first gear at 500 RPM is going to be smaller. So just leave this axis. If you need to rev something out more than 8,000 RPM, I can work with you. I can try to help you out. Obviously, I'm going to try to help you out if it pertains to a 4L80. Now, so we have ideal speed, now we have real speed. Ideal speed versus real speed is what creates our translip. We go to projected speed, plays into that. That's going to go into translip as well. And then we have shift detection. Shift detection is where we determine whether or not what we're seeing is an upshift. So let's put it this way. If I'm in first gear, cruising along, I should be at 0 slip. So I'm going to be in this cell, which is 70. Gear 2 becomes commanded. I'm going to generate a slip. Oh, and look at that. It's going to be between these two cells. Because I should be on our first gear shift, as I went over earlier, we should be at about 38 to 40% or so is what it calculates out to. The resolution's not perfect, so it's pretty well in that range. But anyway, we give ourselves a little bit of a window here, a little bit of a window, a little bit of gap, so that way we're going to be somewhere in here. Now, with us being in here, and we haven't actually commanded the shift yet, you would say that this number for shift detection is 20%. So we go to TM trigger. TM trigger is going to occur when all of these things happen, but what's most important is shift detection. So in shift detection, which is at 20%, when it's below 19.9, it will activate this box, just this one. Now all of these ones are ANDed together, so that also means I'm going to need to have RPM above 2500, TPS above 45%, fuel flow above 100 pounds per hour. If these three and this are all a 1, or they are true, then and this translip timer is true, then TM trigger will be a 1. When TM trigger, here we go. When TM trigger is a 1, when TM trigger is enabled, we will activate this timing table. Very simple. This part is, at least. With this table enabled, based on fuel flow, which I'm going to call load, I will pull some timing. And that timing will pull until translip, until either A, TM trigger is disabled, or translip is 0. If I take this bottom box, I can just make this a 0. So you could have a fail-safe there. But I don't need to. The reason why is because TM trigger, one of the wickets is that it will deactivate at 69.9%. At 69.9%, I am at, here we go, I'm at about 6% translip, we'll say. So what's going to happen is, as that gear engages, translip's going to start coming down. You can see it right there. As translip starts coming down, shift detection is going to go from 20 to 19.9, trigger, go through 0 for a period of time, come back up. These numbers, this 20 here is there for a reason. I'll go over that. It was mainly leftovers from the 6L90 stuff for flare protection and for slip protection, which it did save my transmission once, so I'm happy about that. But anyway, you could take these if you really wanted to and make them 0, it wouldn't matter. So this will come down, and when it comes to 70 and it hits 69.9, it's going to turn off. It's going to turn off this box right here. And with this box being off, big X through it, and because this requires all of these, this table's off. TM trigger is going to turn off. So easily put, if I'm under load, if you look at really what I am at, what I'm telling those boxes is I'm under load. TPS is above 45%. I have a very responsive turbo, so that's not a bad idea to have it down a little lower. RPM is above 2,500, and fuel flow is above 100 pounds per hour. I pump gas, I'm not an ethanol. If you're an ethanol guy, you should probably put it up a little higher. But if it's above those, it will allow the use of this tape. It'll allow the use of TM trigger. It'll allow torque management. Now, I want to turn off torque management a little bit early because I don't necessarily want to pull timing the whole time that those clutches are engaging. I just want to make sure that Translip, as shown here, once it gets close, I'm going to start letting power come back in because ideally I should be good to go. It's momentum as well. Like as you're slowing something down, it's like when you stop, right? Like when you stop at a red light, if you kept the same amount of force on the brakes the entire time, you would come to kind of an abrupt halt at some point. We kind of want the same thing here. We're going to slow it down, get it really slow by taking some power out during this time, and then it's going to put power back to the torque converter. And if, for instance, our engine speed has dropped below input shaft speed, that torque converter is going to flash back up again. Now, you can tune that obviously with how much timing you pull out. If you pull out a lot of timing, you're going to drop below input shaft speed a lot. It's like hitting a really hard rev limiter. But if you don't do that, if you pull just a little bit of timing, you'll still have a little bit of torque converter slip, but it's not going to be crazy. In other words, you're not going to be trying to yank the input shaft up to the same speed as the engine as hard, which means input shaft speed, when it drops, has an easier time doing it. Which also means the stock bottom end, the rods, they live a happier life because they're not trying to force against the clutch packs and the transmission, drop the input shaft speed down as well. So let's just make these 0 just so it's easier to digest. You don't really need that for a 4L80. Essentially, on the 6L90, when you lose a gear, it goes into neutral. Like if you are in 4th gear and 4th gear has either the 456 clutch pack, either has the 456 clutch pack start slipping, or the 1 2 3 4. Not so likely the 1 2 3 4. But if the 456 clutch pack starts to slip, you essentially rev into a neutral. And as you rev into neutral, this was set up to have 20 here. I could have even put 20 here, or 0, it wouldn't matter. I could have put 20 here. And what would have happened is when it hit 19.9, so when it hit about, actually that has to be a higher number. So when it would hit 19.9, in other words, it would just crest over 8. It would go, oh, 19.9, let's start pulling some timing. And that was good because that transmission, before it broke, it was starting to randomly just slip in 4th gear, which made me think, yes, it has hydraulic issues. It also refused to shift into 4th gear sometimes. It was always a little finicky. So it was good that I had that protection in there. But with, like, say, for instance, the 4T80, which is what Calvin Nelson's using in his LS4 powered Talon, when he lost 2nd gear, it goes into 3rd. So it goes into 3rd gear, you're not really going to see this slip here. It's not going to show you this 30% slip. It would show you a negative number. I would just prefer to avoid that side of the table altogether, make things even more complex than what they are. Can you do it? Yes. Do I know how to do it? No, not really. Like, I don't know how to make it work. I would need to have instances where it did actually slip and go negative. I could probably add it in, but it's just not worth my time. So you can see in 2nd gear, that's about a 40% reduction. And then we're safe here, but as soon as it starts dropping below 19.9, so right around like 37.2%, it triggers the timing pull. Now the reason why we have, go back to shift detection, or is it, I don't remember which one it is. Here we go. The reason why TM trigger is linked with this Translip timer is and this translip timer is not big. It's essentially once translip gets above 15, and it will deactivate at 6, kind of following along with the other thing. It has an activation delay built into it though. There's a reason why. When, let's see, where is shift detection? Here we go. When you shift from first to second gear, you are instantly creating, 38 to 43% slip. It's instantaneous. The Holley doesn't operate that fast, but the next time it comes around the cycle and it checks that, those bits or whatever, it's going to be like, oh, we're now all of a sudden at 38%. And very similarly to how this line is drawn as a linear interpolation, it does the same thing. So it goes, oh, you had to have crossed, say I'm in second gear, you had to have crossed 19.9 right here in order to get up here. Therefore, trigger the box, right? Trigger the trap, kill the timing. We don't want that. We don't want to have it actually start looking at this table until Translip has made its way up to here. Now, in order to do that, we essentially have a sacrificial timer here, which once Translip gets above 15 or whatever, it's going to start activating. And you can make this probably like 28, whatever, it doesn't matter. But what does matter is the activation delay. The activation delay can be just about any number, it doesn't matter. It's essentially just telling the shift detection, telling the TM trigger to ignore that first initial line where it travels up. Even though that line is practically instantaneous, it's almost backtracking to be like, oh, I had to have done this, therefore enable the box. So I think that was all I wanted to cover. Yeah, so it's kind of the same thing as the 6L90 stuff. I made it very simple. If there's anything I want to have you take away from this, it's just plug in this stuff here correctly, use the tables from the base map, and just modify the torque management to your liking. That's it. It's pretty simple otherwise. I can't really think of anything else. But if you have any questions, message me in the comments or message me on Facebook. I'm usually pretty responsive. But otherwise, I hope you guys have a good night, morning, whenever you see this, and give it a try. Let me know. I mean, if you hate it, okay. If you think it's useless, okay. Like, it doesn't bother me if you think that. What does bother me, though, is discrediting people's work. So I put a lot of time and effort into all the things that I do, and I field test them before I post results. Please don't come yelling at me, telling me it doesn't work. You probably set something up wrong, or something of that nature. Just let me know. I'm more than happy to help. So if this works for you, awesome. If not, again, let me know. Thanks.